Hello everyone, we're going to be going over EE310 for the midterm, and we're going to just start off with the basics. And so in the beginning, basically from lecture 0, what we started off doing was we talked about signals and systems. So a signal is defined basically as one or more independent variables, and that carries some type of information. So this could be like what I'm talking to you right now. It could be like the height of basically the amplitude of how loud my voice is. That's one common example of a signal. And then a system, on the other hand, is basically it manipulates one or more signals. And what that means by manipulating is it makes some change to the signal. And so we're going to look at this through a block diagram representation. And so for the block diagram, we're going to have x of t, and then that's our signal going in, and then it goes into our system in order to be manipulated. And our system in this instance is going to be h. And then it's going to go to an output y of t. And so if we want to write basically what happens to the signal for the system, our output y of t will be equal to how the system manipulates the input signal. And so yt will be equal to the system and how it manipulates that signal coming into that system. And after we talked about this little intro, we focused on Cartesian coordinates and polar coordinates. So for Cartesian, what we need to know is if we're going from Cartesian to polar, is Cartesian sort of like your rectangular coordinates, where polar is more like the angle and the length of the vector, where the Cartesian is more like the x comma y. So the Cartesian, let's just have an arbitrary vector, okay? Let z equal a plus jb. And when I talk about that, that's basically saying right here that a is our real part. So along that x-axis, where the jb, that's your imaginary part. And that's going to be along the y-axis, so you guys know. And now that we talked about that, let's do some of the conversions between Cartesian to polar and polar to Cartesian. So first, starting out, Cartesian, it's like rectangular coordinates. And so if we have our A and B terms, and those are representing how much we go in the x direction, how much we go in the y direction, if we represent that and want to change that to polar, which is going to be the magnitude and phase angle representation, it's going to basically, for magnitude, be equal to the absolute value of the vector, which is just the diagonal from a squared plus b squared. And then the phase angle is going to be equal to tangent inverse of b over a. And how you're going to see this in an actual representation here is for our Cartesian coordinates, you travel a in the x direction, so I'm just going to have an arbitrary point, call this a, and then you travel b in the y direction because that's along our imaginary axis, so this would be jb. And so what that vector looks like here is it is from the origin, you start always at the origin and you go to the point. And so this vector is z. And that's what's representing this part, the Cartesian coordinates. Then we find the magnitude and phase angle, because that's how you represent it in polar form. So the polar form, how that's going to look like, is basically you have a magnitude m for the vector, and then you have a phase angle here. And that's how you represent Cartesian coordinate and you change it in terms of a polar. And how that looks in the end is it is basically your z is equal to the magnitude in the phase angle. So here's our Cartesian representation, and here's our polar representation. Okay, and now that we've done that, let's look at the polar to Cartesian. And so that's the opposite way, how you convert going the other way. So polar to Cartesian, how that's going to look is it's basically going to have your A be equal to the magnitude in the cosine of that angle, and then B would be equal to m times the sine of the angle. And the reason is because cosine is 1 along the x-axis, so that's going to give us our term along the x-axis, because we know A is how much we go in the x direction, and B is how much we go in the y direction, and that's where sine, when you do sine of pi over 2, that gives you 1. And so when you think of the unit circle, cosine is 1 at along the x-axis, and sine is 1 along the y-axis. And so that's how we go from polar form, which is when z equals magnitude in the phase angle, to Cartesian form. And so the result would be, after this calculation, z equals a plus jb. And so that's how we do the two forms, converting between them. And it just comes from those basic equations we have here, which tells us how to convert between the two. So this one right here takes the length of the diagonal, this one finds the angle, this one finds the x, and this one finds the y term. Okay, now that we covered those, we need to know a little bit about addition and subtraction. So when you do addition and subtraction, the preferred method is Cartesian. So when we are working specifically with, let me put this down, use Cartesian for addition and subtraction. And so what that is going to look like is, if we have two vectors and we want to add them together, we're going to add their real parts together. So that'll be a1 plus a2. And then we're going to add their imaginary parts together, b1 plus b2. If we do the exact same thing but with subtraction now, it's going to be their real terms subtracted from one another and their imaginary terms subtracted from one another. So it makes sense. You use Cartesian form for addition, subtraction, but then you use polar for multiplication and division. So what that's going to look like is, it's going to look something like this, where you have one vector multiplied by the other, so z1 multiplied by z2, and that's going to equal the magnitude of the two vectors, and the angles will be added. For division, that's going to be z1 divided by z2. That's going to be the angles divided by one another. I'm sorry, the magnitudes divided by one another and the angles subtracted from one another. And so that's the common techniques. And now we're going to talk a little bit about special properties and how to use these. And so for the special properties, how we're going to look at them is we're going to have two vectors, z1 and the conjugate of z1. And so let's just look at an example for now. So z1 is equal to, and it's going to be a1 plus jb1, and z1 conjugate, I'm going to just put that over a bar for conjugate, is going to be equal to a1 minus jb1. And so if we show that here, in a graphical analysis, what that's going to look like, I'm just going to choose arbitrary points, but A1 here is how much we go in the x direction, and then B1 is how much we go in the y direction. And so if we draw Z1 real quick, it's going to go from the origin to that point. And then Z1 conjugate is A1 in the x direction and B1 in the negative y direction. So it's going to be minus B1. And so it goes from the origin and goes in this direction. So this is Z1 conjugate. Now that we talked about those two, let's look at what we mean. So when we say Z of 1, we can write that in terms of polar, which would just be the magnitude of how long that vector is and the phase angle from the origin. So this would be theta in 1 here. And then Z1 conjugate is going to be the same magnitude, but the angle is going to be in the opposite direction here. So it's going to be minus theta 1. And then if we add the two together, Z1 plus Z1 conjugate, what that is going to give us is basically, if you look at the two and add them together, well, let's see, M1, and then the other one, it would be M1 times M1, if you remember from our property back here. When you do the two added together, what that's going to give us is, if we convert it, is it gives you twice times the real part, sorry. So it actually be 2A1. So it'd be 2 times the real part here. Okay, I just 2 times A1 here. So this is A. And if you do one of them subtracted by the other, so what's going to happen is you're basically going to get just the imaginary part. And so these are just two conventions to be familiar with. But if you multiply both of them, so if you multiply the vector by its conjugate, you get, then here was where I was trying to get, magnitude squared of the vector. And if you divide the two, Z1 divided by Z1 conjugate, what you're going to get is M1 angle of theta 1 divided by M1, and then the angle would be negative theta 1. And if you just do that, the magnitudes divide, so that would just be 1. And then it'd be theta 1 minus negative theta 1, and so that would be 2 theta 1. And so we can prove that one easily. The one up here, we can go back and prove it if we just do M1 times theta 1, all multiplied by M1 negative theta 1. And that will give us M1 squared, and then you add the angles together, and then that's how we got angle of 0, because theta 1 plus negative theta 1 will give you 0. And so we can just write this as M1 squared. And then these two specifically come by, if you add the vectors together, tail to tail, it's just going to give you 2A1, and then if you do the subtraction of the two, it gives you 2 times the imaginary term. Now that we talked about that, we're going to do one example in the notes that I thought was pretty good because he might be tested on this, and it's a good one to be familiar with. So this one is going to be x cubed is equal to 1. So you probably wonder, how should you go about solving that? Well, what I do when I see this is I know you can represent that specifically by in polar form, because it has a magnitude of 1 and has a phase angle of 0. And so what you're going to use here is sort of like Euler's identity, which, but in a sense, you'll see after why I say that. But we have x is equal to, and then m, and then the phase angle. So the magnitude and the phase angle, remember, and you can also write this in MEJ to the theta. These two are interchangeable. You can go from one to the other. So that's an important one just to recall to spark your minds a bit. We talked about that in class. And so what you're going to have here is if you cube this, remember if you do x cubed, that's going to basically be m cubed, because it'd be the magnitude and then all the phase angles added together. Because it'd be 3 of these. So then the magnitude times the magnitude times the magnitude, and then a phase angle plus another phase angle plus another phase angle. If you just wrote this out 3 times and multiplied all of them together, you get this. And so we can simplify this just to m cubed and then 3 theta as our angle. And what we set this equal to is, because this is our x3 term here, we set it equal to 1 with a phase angle of 0. And so if I just rewrote this here, our m3 phase angle of 3 theta is going to be equal to, and then it's going to be our 1 with a phase angle of 0. So that's how you derive those for that equation. But remember, you can do a 360-degree turn in the unit circle. So that would be 2k pi, because that represents 360 degrees, 2 pi. And then you can either go once around the circle, twice, 3 times, 4 times. That's what k represents. And so what's going to happen is basically, if we look at this equation in particular, we set the magnitudes equal to each other. So m cubed is equal to 1. And then we set the phase angles equal to each other. So 3 theta is equal to 0 plus 2k of pi. And then if we set those equal to one another, so I get m cubed is equal to 1. So that just means m is equal to 1 if you take the cube root. And then 3 theta is equal to 0 plus 2k pi. And now if I solve for this, if we have k equal to 0, that's going to be 0 is equal to 3 pi, so that would mean that, 0 is equal to 3 theta, that means that theta is equal to 0. But if k is equal to 1, so that would be 2 pi is equal to 3 theta, so 3 theta is equal to 2 pi. And then you just solve for theta, you're going to get theta is equal to 2 pi over 3. And then if we have k is equal to 2, that's going to give us 3 theta is equal to, and it's going to be 4 pi. And then that means theta is equal to, and then 4 pi over 3 if you simplify. And now that we covered those in particular, if we go back now, let's say if you went k equals 3, you're going to see that it starts to repeat itself, and just watch. Or if you do k equals -1, it repeats with k equals 2. So let's just do an example so you can see why I didn't choose other k values, because they would give us just the exact same solution we got for theta. So if I chose k equals 3, that would mean going back in here, you would get 3 theta is equal to 6 pi, and that would mean that theta is equal to 2 pi, and that is the exact same on the unit circle as 0. And so that's why we don't choose other k values, because it's just going to repeat these solutions we got for theta equals 0, because 2 pi away from that is just 2 pi, and then theta equals 2 pi over 3, and then theta equals 4 pi over 3. So those are the 3 solutions we have, and that makes sense since this is an m cubed. When we started out, the big thing you should notice when you start out with this problem is that it's raised to the cubed. That means you have 3 answers to it. And now that we have resolved and found our 3 solutions, we need to plot this. And so if we're going to plot this specifically, what it's going to look like is, well, the first one is at an angle of 0 and the magnitude is 1. And so let's just say that's my magnitude of 1, and then the angle is 0. So 1 angle of 0. This one here is 2 pi over 3 and the magnitude is 1. So that would be 1 angle of 2 pi over 3. This one, it's going to be theta equals 4 pi over 3, magnitude's 1. So here we go, 1 angle of 4 pi over 3. And that's how we got specifically all of our solutions to this equation. Now that we have covered that, I want to get a little bit into Euler's formula, because you'll see that a lot in this class. So Euler's formula, what that covers is, going off, is it relates an e to an imaginary term and puts it in terms of cosine and sine. So just going to Euler's formula, it looks like e to the j theta is going to be equal to, and then it's cosine of theta plus j sine of theta. And just know if we had a negative in front, that would cause the negative to be here. And so Euler's formula is a big one, and what you can derive from it is these relationships, which are cosine of theta equals 1 over 2 e to the j theta plus e to the negative j theta. You can get sine of theta is equal to 1 over 2j, and then that's e to the j theta minus e to the negative j theta. And then you can also get the third one, which is e to the z. And remember, z was our vector, a plus jb. And so we can rewrite that as e equals a plus jb. And then you can separate these two into e to the a, and then multiply by e to the jb. And that's equal to e to the a. And then remember here, now we have a Euler's identity for the e to the j beta term. So this one here, it's going to be cosine of b plus j sine of b. And now that we got that, if you multiply it out, you're going to get e to the a cosine b plus j e to the a sine of b. And now we've seen how you can write these ones, and in particular, I want to look at these two here, deriving them, because that's an important relation in this class, the cosine and sine terms. So let's just practice a derivation. So for the cosine term, let's look at that one. So if we have e to the j theta, we know that's equal to cosine of theta plus j sine theta. And then if we have, let's write e to the negative j theta is equal to cosine of theta minus j sine theta, due to that negative sign being in the e term. And if we add these together, what we're going to get as a result is e to the j theta add e to the negative j theta is equal to, and then it's going to be 2 cosine theta. And the sine terms cancel with each other because it's positive and negative. And so then when you solve for this, it's going to be cosine of theta is equal, just divide by 2. So that would be all this term in the numerator, e to the j theta plus e to negative j theta all over 2. And that's how you solve for cosine theta. And now if we're going to do sine of theta, how are we going to get that one? Let me derive that right below. Same process, but for sine of theta. So if we have, in particular, e to the j theta, that's equal to cosine of theta plus j to the sine theta. And if we have e to the negative j theta is equal to cosine theta minus j sine theta. And instead of adding the two, let's do a subtraction. And so if we do subtraction here to this whole term down here, it's going to change the sign. And so e to j theta minus e to negative j theta equals cosine theta minus cosine theta, so those cancel. And j to the sine theta minus negative j sine theta, so that would actually be j2 sine theta. And now if we divide by 2 on both, 2j on both sides, what you're going to get for sine of theta is going to be equal to e to the j theta minus e to negative j theta all over 2j. And that's how we derive these relationships up there. Oh, sorry. Let me push that up. So basically what we did here is we had our e to the j theta equal to cosine theta plus j sine theta, and we subtracted e to the negative j theta from it. And when we did that, we got this result, and then we just divided by 2j on both sides. That's how we got sine of theta. And now that we covered all that, that was pretty much the basic math review that you should have seen in it. And now that we covered that, I'm going to go and start into the actual signals lecture number 1, because this is just the summary of what you should have learned. And now as we hop into signals 1, this will be focusing on what is a signal. And so, lecture 1, signals 1. And so when we look at this, a signal, remember I told you guys, is basically a function of one or more independent variables. And so how I like to think of it is we have our independent variable, usually t, and then our function x of t here, and then our signal is going to look something like, like some weird waveform. You have those commonly. And when we say x of t, we mean x is the signal and of the independent variable t here. And now that we covered that, we're going to get into the different ones you will see a lot of times in this class, which is like unit ramp, unit step, all those which are popular. And so what we have here is we have the different types. So let me break them down for you. A constant DC signal is going to look something like this, where we just have our x and y axis, and the constant signal is going to be something like y equals 1 or something, something very basic. So here, if we're just writing it in x of t as our y-axis, we would just say x of t equals 1, and that is our signal there. It's a constant DC signal. It doesn't change at all with time. Now that we covered that, let's get on to the next signal here. So next one I want to talk about is unit step. So the unit step, this one is an important one. You're going to see a lot of times. It's defined by u of t is equal to, and then it's 1 for time greater than 0, and it's 0 for time less than 0. And so if we draw this out here, and we graph it, what we're going to get is it's going to step and jump up. And so we don't know specifically what it's defined at time equals 0. I drew it here just to show you that we don't know. There's some type of jump there, but at time greater than 0 here, so when it's passed, it's at 1, and at time less than 0, it's at 0. But in between, there's a jump there. And some people define the in-between as 0.5. Some define it as an impulse, but we did not define it for this class, so I would not define it. And then the next one we talk about is unit ramp. Unit ramp is basically, we symbolize this by r of t, and it's going to be equal to t for time greater than or equal to 0, so it's just a constant increasing line, or it's 0 for t less than 0, so nothing happens before time equals 0. So here, what it's going to look like, if we draw it out, is it's going to be a ramp for time greater than 0 with a slope of t, and then it's going to be 0 here for time before. So I'm just going to say t here. This is how, if I want to just call this ut actually, and then rt, that might be better, just to show that this is the ramp, this is the unit step. And this, you'll see how we can modify these signals by making operations on the independent and the dependent variable later on. Now we talk about unit ramp. The rectangular pulse, that one is basically rect of t is equal to 1 and 0, and specifically for the absolute value of t, which is less than 1/2, and then for the absolute value of t, which is greater than 1/2. So here, what we're going to see is that the signal looks sort of like a rectangle. So at -1/2 and a 1/2, basically it's going to be like a little rectangle here we have, and it's going to be equal to 1, and then at other times it is 0. So that's what your rectangle looks like. So it's 1 for time in between -1/2 and 1/2, and then 0 anywhere else. Okay, now that we talked about the rectangular, we have two more, which is the sinusoidal. Which is basically x of t is equal to a cosine frequency times t plus the phase angle. So here, a is the amplitude. We have the angular frequency, so I'm going to write frequency here. And then we have the phase angle theta. And now if we specifically look at what our graph is going to be, it's going to look like, because we have the cosine here, I'm just going to draw out what normally, and here would be like how high our amplitude is, and then the phase angle would say if it's shifted over by any amount, and then our frequency would determine how that period of the cosine is going to appear like. Because if we recall, the frequency, it's going to be the inverse of the period. And so now that we talked about sinusoidal, the next one you need to be familiar with is exponential. So exponential looks something like this, where it is x of t is equal to e to the negative at. And a, what that symbolizes is it's the speed of decay. And now that we went over what a is, let's look at what this graph is. And so our exponential term it's going to look something like a decreasing exponential where it goes through. Sorry, let me get this right. And it decreases pretty rapidly. And so just A tells you that speed of decay that you're going to see on that graph. And so that covers the main ones you need to know. So starting back up from the beginning, the constant DC signal here is just a constant you have at your output graph. And then for the unit step, it's just a step at time equals 0 to 1. Then the unit ramp, it's going to be a ramp basically for time after 0. And the rectangular pulse is a little rectangle from -1/2 to 1/2 in sinusoidals, a sinusoidal waveform which has amplitude, a frequency, and a phase angle, and an exponential will tell you how much the speed of decay is, and that's modulated by the A term in that equation. So now that we covered all those, we're going to get on to how you can do an operation on a signal. So let's look at signal operations. And so for the first one, if we have signal addition, it's going to be y of t is equal to x of t plus b. And so what does that look like? Well, if we have our original signal here, let me draw it, and then I'll show the difference in red. So if we just have our original signal here, it looks something like this. This is our x of t. What's going to happen is if b is positive, it's going to shift it up, but if b is negative, it's going to shift it down. So I'm just going to say my b is positive in this case, so it's going to just shift it upwards. And so then this is going to look like x of t plus b. If it was negative b, then it would shift it downwards. And so this is signal addition. And now we're going to get into the next one, which is signal multiplication. So I'm just going to write here up or down. So be up if it's positive, down if it's negative. Signal multiplication. So what you're going to see is y of t is equal to some constant multiplied by the signal. And so if the constant is greater than 1, it's going to be an amplification of that signal. If it's between 0 and 1, it's going to make the signal smaller. And if it's then less than 0, the signal is going to be inverted across the x-axis. And so here, if we draw it out, and let's say we have the signal, again, our original one, which looks like this little waveform here. And I'm just going to call that my x of t. And if we amplify this by 2, so this would be 2x of t, it's going to go upwards, then it's going to go downwards, upwards, downwards, and it's going to reach twice the amplitude for this. So it's going to be basically 2x of t. And now that we talked about that, if this term is negative in front, that's going to cause the signal to flip. And so if I had a negative x of t, it's going to just be flipped across here. You can see it's flipping basically the terms. So our negative x of t, that's what this one represents, and it's just flipping it across the x-axis here. And now that we talked about what those can do, just a summary real quick is a greater than 1 amplification between 0 and between 0, not including 0, and 1, it's attenuation. And for a less than 0, it's inverted. Okay, now that we talked about that, we're going to talk, sorry, I noticed I just should have said not signal, because that'd be more than one signal. It should be scalar addition and scalar multiplication, because we have a scalar multiplying by it and we're adding a scalar just to the value. Sorry, I got the terms mixed up. You'll see signal addition actually coming up pretty soon. And so now that we talked about that, let's go to combine scalar addition and multiplication. And so how are you going to know which one to do first? Do you do multiplication first or do you do addition first? And so this is where it comes in part. So if we have the combination of the two, addition and multiplication, what you need to do basically is you'll have like a term, it looks like yt is equal to a to the xt plus b. Well, you have multiplication here, scalar multiplication, because you're multiplying the signal x to t by a, and you're adding the scalar b. And so what this is going to be actually is first you should do the multiplication, then you do the addition. And that follows the same order. Multiplication has priority, right, over addition in PEMDAS. So follow that exact same format when you see these two. Now that we talked about that, we're going to do signal addition now and signal multiplication. And so for signal addition, you have to have more than one signal, right? So this is going to be like y of t is equal to one signal plus another. That makes sense, right? Signals two, one or more adding together. And then we're going to draw this out. And so I'm just going to have a unit step function here for my x1 of t. And then I'm going to have a ramp for my x2t. So how do we add these together? Well, let's look. Before times 0, they're both 0. So adding them together, it's going to be 0. But past times 0, it's going to be 1 plus, and then, so you're going to add the red and the pink curves together, what their values are. So 1 plus 0, so that's going to just be 1 for my yt. And then if we look, the red remains at 1, so 1 plus, and then it's whatever the pink signal is, because it's red plus pink equals the green, the output. So 1 plus, and then whatever value we have for here. So it just looks like shifted up 1, and then here shift up 1, and then here shift up 1. So the addition of the two signals, if you just look at it by point to point, it's going to be the two added together here. So you just add the red and the pink curves together, what their values are. Now we're going to do signal multiplication. And so for signal multiplication, you're going to have y of t is equal to x1 of t multiplied by x2 of t. And what that's going to look like is basically you have the two signals multiplied by one another, and you just go point to point. And so let's do another example here where we're going to have let's have a rectangle actually for this one. So rect, and let's have a unit step. So this one's going to be x1 of t. This one here is going to be x2 of t. And so my output, yt, if we just multiply these two, well, 0 times 1 is 0. 1 times 1, so here, 1 times 1, 1 times 1, this produces 1, then here it's 0 again. So basically you have 0 before time 0, and then it comes to 1, and then goes back to 0 here. And so you just multiply the two by each other, and you go point to point. So that's my yt. Now that we talked about signal addition, signal multiplication, we need to talk about time shifting. And so time shifting is when you shift it either to the left or the right. And so now that we're going to look at what happens to the independent variable. So that's where we're going to see time shifting occur. So time shifting, it's basically when you have your yt, it's going to be equal to x of t minus large t. And the large t, when it's greater than 0, so t is greater than 0, you shift to the right. But when it is less than 0, shift to the left. And so that's how we have the two for time shifting. And so what we're going to have here is it's going to look like this. So if we have our original signal, and I'm just going to use the unit step for this, u of t, if it is greater than 0, so if we have ut minus 1, so 1 is greater than 0, we shift it to the right. U of t minus 1. And then if it's less than 0, so u of t plus 2, because that would mean t is actually, large t is equal to negative 2. That would be over here somewhere. And so that would be u of t plus 2. Because this is where t is equal to negative 2. And then this one was where t is equal to 1. Okay. Now that we covered that, we're going to go over time scaling. And time scaling is basically, are we going to compress the signal or are we going to expand it? So this is when your yt is equal to, and then it is x alpha t. And this is when alpha is greater, so absolute value of alpha is greater than 1, the signal is compressed. But then when alpha is between 0 and 1, the signal is expanded. And so it's either condensing the signal when it's greater than 1, or it's expanding it when it is in between 0 and 1. So I just want to do an example here so you can understand it, and I'm going to actually mark the units on this one. So we're going to have 1, 2, 3, 4, 1, 2. And so here's our 2. So this is going to be basically, let me just draw our arbitrary signal here. So it's going to look something like this. Triangle. And so this is what our x of t looks like. If we want to make this signal smaller, so it's compressed, this would be x of 2t here. But if we want to make the signal larger, then it's going to be x of 1/2. So that's going to go to 4 here. And so this would be x of 1/2 t. And so that is how you do expansion or compression of signals. And so you can see here, when we compress it specifically, because this is time 0, 1, 2, 3, 4, and when we had -1, -2, -3, -4. When we had x of 2t, that caused it to go from -2 to 2, which is 4 in total, just to -1 to 1. So it cut it in half, where when we had x of 1/2 t, that made the signal twice as long. So from it originally being from -2 to 2, which is a whole length of 4, it went from -4 to 4, which is a whole length of 8. Then we have time reversal. And so time reversal, what that is going to look like is basically time reversal. It's going to be yt is equal to x of alpha t. And this is going to be when alpha equals -1. The signal is flipped about the y-axis. And this is for any negative number. I just, you can have -2 or -3, negative whatever, but if you just have like -3, -2, remember that 2 or 3 in front, it's going to cause the signal to be more compressed when you flip it over, just so you know. But let's look at what this does. So if I have a signal, let's say, and I'm going to have a unit ramp signal, so it looks something like this. It then goes up, so it's R of t, my unit ramp. My R of -t, what that's going to be is it's going to be flipped about the y-axis. So here's R of -t. And that's how we got that signal. Now that we have that, we're going to go on to combined operations. And so combined operations, what those are going to look like. So basically, if you're given, I just want to show you guys how you can simplify it in order to get it to what you want. So I'm just going to use some examples here for combined operations, but you'll remain in the same order as we have been doing, where you first are going to do the multiplication, then you do the time shifting. And so what that can look like is, let's say you have y is equal to, and then it's x alpha t minus beta. It's given in this form here. And an example of this could be y1 is equal to x2t minus 3. So which one do you do first? Do you do the scalar do you do the scalar multiplication first, or do you do the scalar addition? And remember, I always told you guys do scalar multiplication, then addition. Here, when you have it in this format, if you want to graph it, what you need to do is you have to pull it out so that it actually gets in this form in order to do multiplication, then addition. So if you rewrote this so that would be x of, and then you're going to take out alpha term, and then you're going to have t minus beta over alpha. And then now what you can do is you can do the multiplication first by that scalar, and then you can do the addition. And so if we were to rewrite this one down here, it'd be x, and then it'd be 2t minus 3 divided by 2. And so we first do this multiplication here, then we shift it over. Okay, now that we have done that, this is an important one. I always like using this format because it makes it easier. So just remember, take out that multiplication term so you can turn it into this format. So you can do multiplication, then you scale it. And so that is what you need to know for combined operations. And now that we have covered that, let's go on to an example here where we might see it. So let me just use one example here where you have to do a combined operation of the signals. So here we're going to have y of t, so example, y of t is going to be equal to 2e to negative t over 2, and then it's going to be u of t minus u of t minus 1. So here, what it's going to look like is this. And so let's first look at what this is. So it's a combination of signals. We have a term here, we have a term here. Well, it looks like we're going to multiply this signal by this signal, right? And so what I would do first is I'd be like, okay, if we know this is one signal here, and we know this is another signal here, let's just plot them separately, then do signal multiplication. So we have ut minus ut minus 1, so here would be 0, 1, and so this would be our ut and then ut minus ut minus 1. And then our 2e to negative t over 2. How would I know specifically? We know it's a decaying exponential because there's an e to the negative term. And then we know basically the decaying term, remember, if I rewrote this into 2e to the negative 1/2 and then t, we know this term right here is going to tell us the speed of decay. The 2 is basically just going to be a scalar multiplication of this. So this means there's a smaller speed of decay since it's only 1/2 here. And so remember, E always intersects at 1, but since it's multiplied by the scalar 2, it's actually going to come through at 2, not 1. And so here it's a slower decay, so it's going to look something like, it's going to look something like this, slowly decaying. It's not as fast. And so, just another term here. Now that we talked about what it's going to look like, 2e and then a slow decay because it's only 1/2 and it's a decaying exponential. Now we do multiplication of the two signals we have here. So right here it's 0 times whatever, so 0 times whatever is going to give you 0. And then it looks like after that point, it's going to be this signal multiplied by the other, so 1 times 2. So just do it by dotting it. And then it looks like 1 times whatever this is, and then 1 times whatever this signal is. And then here it's going to be 0 times whatever that signal is, so here it comes back down to 0. So it looks like it's just going to follow this signal in between 0 and 1. And that's going to give us our yt term. Okay, now that we talked about it, how those signals overlap and how you do the signal multiplication, let's go over to now the second part of signals. What we need to know, what else we can do with them. So this is going to be classification of signals. And so this will be lecture number 2. Okay, so classification of signals. What's going to be is a signal, remember, is a function of one or more independent variables. And so when we're looking at signals, we can either have continuous or we can have discretes. And that's an important one to know about, is if we're going to have a discrete signal or a continuous signal. So let's look at what continuous versus discrete is. And I feel like this is best done through pictures, just seeing what it looks like. So continuous signal, it's basically the function can assume a value at any time. And so here, if I have my signal and it's just going along and along and along, this is continuous because at time 0 to whatever time is here, it can assume a value. So we say this is continuous. Function can assume a value at any time. And then on the other end, we have discrete. And so it could look something like this. And basically for discrete, the function takes samples. It can't have a value at every time. It takes it at like timed intervals. Like if you think of like a clock, it only changes every second. Or you can think of, because it only updates like, or a third, I guess like the weather on your phone, it only updates every probably few minutes when they get a new reading in, and then that signal sent out. So for the discrete, the function takes samples at specific times. And so what we're going to see now is there's a sampling period. And so when we say our discrete signal, it basically, we can write it as x of t is equal to, and then, oh, sorry, x of t where t is equal to, and then this would be k times ts. And ts here is our sampling period. So sampling period, that could be like you're taking a sample every hour, you know, for the weather, or basically it's just like how often is it going to occur, how long is that period in between when you take each sample. And so basically, if you have more samples, it's going to take up more memory. And the reason is if I want more samples, let's say, like maybe I don't want the weather every hour, I want it every minute. And so then that, if we're just looking at specifically one period, I'm going to have like maybe like 60 of these in like one period, just like measuring what the weather is and going up there. And so that's what like your discrete would be like if you have a lot of samples. And so that is, if you have more samples, it's going to have a smaller sampling period. But if you have a few amount of samples, that means you have a larger sampling period. And so now that we talked about that, common notation, what happens is if we know specifically the sampling period here, we can just write it in terms of k. Since the sampling period is implicit, we don't need to send that information over anymore. So we can just write a discrete signal in terms of k here, and that means the whole discrete time signal. Because the sampling period, if it's every hour of the day, you already know that. And so you just need to know the value specifically at that hour, because you can find out the hour because it's just the same period. And so you can say then maybe at hour 0, at hour 1, what is the value of the temperature? At hour 2, what is the value of the temperature? And so forth. And so that is in contrast to a continuous, where continuous signals, we often use the notation x and then parentheses for t, because it is taken at any time of that, and then the period, it relates to that, but basically all you need to know is that a discrete signal takes samples at every single sample period, and it will record that. And so we use this x and then this notation of the brackets around k to indicate that the sampling period is implied, and this just tells you specifically at those integer values at time 1, time 2, time 3, what was the value. Whereas continuous, we use this notation to signify that at any point in this signal, you can determine its value. And now that we've done that, we're going to say a signal a little bit about it. You have to quantize it. And so a quantization of a signal is basically when it can only assume certain values. And the reason we use quantization is because sometimes when we go here and we look at our discrete signal, so I'm going to just draw out a signal for you and show you what quantizing would be. So say I have this continuous signal and I want to quantize it. So here's our signal. And you're going to quantize it. And so when you have quantized, you have certain levels, like quantum levels. There's only certain values it can assume at that level. And so here, we're going to say that if you have this, maybe it can assume a value up here, and then it can assume a value here, and then it can assume a value at 0. So it has these specific quantum levels where it can measure. Well, the signal's going to be a little bit, it doesn't appear exactly like the original. And the meaning I get behind that is it's going to look something like this, because we can only assume certain values, we can't assume the entire waveform. So the quantization of this would be something maybe like this, and then up, down, and then here we go. And so this would be like the quantization, because we can only assume certain quantized levels for the signal. We can't assume all the values. So this, if we're just going back, this might represent 1, 0.5, and 0, and then negative 0.5 and negative 1. And so that's what quantization means of the signal. It's basically, it assumes certain values, whereas this one, this original signal was 0, you could have 0.01, 0.10, and then all the way up to 1.00. And then you could go negative 1.0 from 0, negative 0.01, and you understand it. What I'm trying to say is that you can assume any value here, but this one you can only assume certain values, so we have the quantization of the original signal here. And a signal is piecewise continuous if it has discontinuities. And what that means is the signal values jump at infinite values a time. And so what we mean by that is it's piecewise continuous if you have continuous means that the continuity test, if you remember that, if you have a pencil or something that looks like this, but if it jumped at this moment and it just kept going on and on, well, if we do the pencil test, there is a value at every time, so it's continuous, but this is a piecewise discontinuity where it jumps up. So this is what we call piecewise continuous. And then I just want to have this one note. What's the difference between sampling and quantizing? Because we say digital signal is sampled and quantized, so what does that mean? Well, when you sample it, let me draw this out, and I'm going to use different colors for you guys just to understand it. So we have this original signal here. And we have the we have the sampling of it. So let me just show you sampling, and that's going to be in red here. Oh, sorry, not red, pink. And so at these sampled periods of time, what it's able to take, like here, maybe here. And so you can tell the sampling's right on the specific value. But the quantization of this, the quantized values are limited. So maybe our quantized values, it can only assume 0.5, 1, negative 0.5, and negative 1. And so then here, the quantization is pretty good. It's right at that value where it was sampled. Here it's good, but here the quantization will only occur here, so there's a little bit of an error here. It won't take on that actual value. The quantization will occur at negative 0.5, negative 1. It won't occur here, but it will occur down here. This one, it will occur probably still at negative 0.5. That's closer. It will occur at 0.5 for this one. It will occur at 1 here, and then there's no more. So it's going to look something like this, the quantized signal. And then just so you know, an FYI, it's not going to look exactly like what you had in the discrete. So you have to take it only at those certain levels where it's able to record the information. And so what we like to do a lot of times is we sample the signal, then we quantize it when you do digital signal processing. Okay, now that we covered that, we're going to go over to what is the difference between continuous, discrete, analog, or digital. So I'm just going to give you guys two examples here. And so let's say we have something that is looking like this. And so what this is this is discrete because it's only taking it at samples of time. It's not every single value. And so we can say this is discrete, it's not continuous. Is this analog or digital though? In digital, it's either 1 or 0. There's 2 states you can go between. We see there's multiple states here. It can be 1, 0.5, 0.25, negative 0.25, negative 1, negative 2, and you can tell it's not set between either on or off. And so therefore this signal here we say is discrete and also an analog because it is not set between 2 states like a digital signal would be. And now if we have this other one here, where you see this usually like from your function generator, it produces a square wave. And so that would be something like this. Well, there's 2 states here. It's like 1 and negative 1. So that, I would say right there, that should be a clue. This is a digital signal. And it's continuous because there's a value at every single time. And so this is continuous and digital. So those are the summarization of the two. Now that we went over that, we need to talk about the difference between casual, anti-casual, and non-casual R. And so casual, what is that? So a signal is casual here. So I'll do. So sorry. Causal, not casual. Causal. Always use causal. So causal means it is x of t equals 0 for time less than 0. It is non-causal for x of t is not equal to 0 for any t. Or for basically, you'll see what I mean when I say this. But then anti-causal is just the opposite. I think of it as anti is opposite. So literally just write the exact opposite of this. X of t equals 0, and then the bounds are opposite. T is greater than 0. So this one is just the opposite of this one. That's how I know the difference. And then non-causal just doesn't follow any pattern at all because it's it doesn't follow a pattern. And so this would be your causal signal. So if we say x of t equals 0 for time less than 0, here it's 0, and then after that we don't care. So this is causal. And then let me real quick, I will be right back to plug in my computer, so give me 1 minute. Okay, let's get back to it. So if this is causal, if for any time less than 0, it's 0. Anti-causal, let's just look at the exact opposite. So if it's anti-causal, that means exact opposite. Anytime past time equals 0, it is 0. And then non-causal, it's not causal or anti-causal. It just has no pattern to it at all. It does not assume a specific value. So this is what like anti-causal might look like for your signal. Sorry, my pen was dying out there, but it wouldn't have more. Sorry, this is non-causal. Because it follows no pattern. Now that we covered that, let's get into what's an even and what's an odd signal, because this is a really common one you're going to see. And this pops up a lot. So even versus odd. So an even signal here is your x of t is equal to x of negative t. That means if you plug in a negative value for t and it produces basically x of t again, then it is an even signal. However, if you have an odd signal, if you plug in a negative value for t, it's going to pop out a negative to cancel with that one in order to equal the original x of t. In the even signal, what you need to know is it's symmetric with respect to the y-axis, but an odd signal is symmetric with respect to the origin. And so we have those two differences by which a signal can either be odd or even. Now that we talked about that, let's look at it graphically. So an even signal is going to be symmetric around the y-axis. So that means maybe I have this triangle. It's symmetric on both sides. You can flip it and produce the other side. Sorry, it's not exactly, but you know what I mean by that. So this is even. Whereas we have a odd signal, and oftentimes you'll see this with sine waves, because if we draw it out this way, that was a really bad drawing of the sine wave, but it is symmetric with respect to the origin, because you can just, you flip it, then you flip it back over. So you flip and flip, and then that's going to produce your original signal you had on the other side. Where the even signal, you literally just flip it over. And so that's the difference between the two. Odd signal has a flip around the vertical axis and the horizontal, where even's just around the vertical axis. And so now that we covered that, we're going to look into even and odd components of signals. And so a signal can be written as a sum of its even and odd components. And for this, what we like to say is x of t, which is our signal, is going to be equal to the even part added with the odd part of the signal. And so the even and odd components of the signal, if we look at this, x even of the signal is going to be equal to, and then 1/2, and then x of t plus x of negative t. And so then where our odd signal is going to equal 1/2, and then it's x of t, and then minus x of negative t. And so basically, the even and odd components, if you add them together, you can produce your original signal. So it's just trying to show you that you can make a signal out of its even components and its odd components. Just if you know the beginning 1/2 x of t, then the other part is just given. Remember when we defined even, it was x of negative t produces x of t. And so then if we know that specifically for a signal x of t plus, okay, this is a really easy proof. Because if we know for even, this is just x of t, right? And so then that's going to produce x of t plus x of t. So that's 2x of t divided by 2. That just produces x of t. And then here, if we have an odd signal here, this is just going to be x of t. So this is going to be x of t plus x of t. So that would be 2x of t divided by 2. That just equals x of t. And so you can just derive those really easily from that relationship, that if you know what an even signal is defined as and what an odd signal is defined as. And so that's how you can go back to it. And so if we were to actually do one where we did the even and odd components, basically it would look something. So let's try an example, because I feel like that's where we need to practice with. And this one would be y of t, so our yt is defined as 1, 0. It's 1 for t greater than 0, and it's 0 for t less than 0. And so our signal is going to look something like this. And so this is our y of t signal. And now we need to get the even and odd components for the signal. So for even component, if we like to think about it, what is it going to look like and what is the odd component going to look like? Because they have to add together in order to produce the result. And so basically, if we go back looking at our definition, what we're going to have, let's see, so the odd signal, so if I just have my odd y, odd of t is going to be equal to, and then this would be 1/2, just plugging it in for our odd component here, and then y of t minus y of negative t. What is this going to look like specifically? Well, if we graph it, what's going to happen is we're going to have, where's our even one? So let me use a color here. And if we graph the odd signal, it's going to take on the value specifically. It's going to be y of t times 1/2, and then it's going to be y of negative t for the other one. So let's look at this. It would be okay, I got it. So this would be distributed 1/2 yt minus 1/2 y negative t. And that's going to be our odd part of the signal. And so let's look at this. Well, yt is 1 for time greater than 0, right? And so when time is greater than 0, it's going to be 1/2 times 1. So that's going to be 1/2 here. And then for time greater than 0, this part is going to cause a flip. So it actually flips over to the other side. And then it is a negative 1/2. So it actually looked like this, flipped over to the other side, but it's a negative 1/2 multiplied by that. It's negative of the original. So it would be flip the original, which is the red curve, flip it over to the other side, and then multiply that by the scalar of negative 1/2. And that is going to produce your part down here, which is negative 1/2. Okay, now that we have that one, so the odd component of the signal, let me then now connect it right here. So this is y odd of t. Now let's do the even part of the signal. So the even part of the signal, y e of t, is going to be equal to 1/2, and then it's y of t, and then it's going to be plus y of negative t. So distribute it out, and what you're going to get is 1/2 y of t plus 1/2 y of negative t. And so if we want to think of this, oh, sorry, didn't notice it was cutting off. What's going to happen for even part of this signal is it's going to be 1/2 of yt here, so it's going to be 1/2 on this part. So that's what satisfies this part of the equation. And then this one, it's going to flip the signal over, and then it's going to multiply it by 1/2. So it's going to flip it over to this side, flip the original yt over from here when it's greater than 0, and then it's going to multiply it by 1/2. So it's actually going to look like this, and it's going to be a constant line here. So if we add the two signals together, the green and the pink, it's going to produce the red here, because for this section, a positive 1/2 and a negative 1/2 are going to cancel to 0, because remember, the even part was 1/2 before time equals 0, and the odd part was negative 1/2. So those cancel to 0. And then here it's 1 for the red signal, which is because both the even and the odd signal were 1/2 at this point. So that's where we got the 2. So this was 1/2 and the even was 1/2. And then so comma y even t. And so 1/2 plus 1/2 produces 1. So that's how we got the unit step from deriving it graphically for the even and odd functions. Now we're going to look at periodic. And so how is the signal periodic? And so now that we covered even and odd, a periodic signal is going to look something like this, where it has a repeating pattern. And the most common one you're going to see is cosine and sine waves. And so this would be something like this. And so the smallest period is going to be when one cycle completes. So even though you could say this is a period here where it completes 2, the smallest period is going to be here. And we call that the fundamental period. And so the fundamental period, basically what you need to know is it's whenever you have to find it out, the fundamental period is just the smallest one it can take on. And there's a relationship that says it's always given by, I just want you guys to be familiar with this terminology, is when you see a signal, maybe it's like y equals, and then it is cosine of 2t or something, you know, or maybe it's pi over 2, whatever, times the independent variable t. This should be your big factor, where in order to find the period, you use the equation 2 pi divided by whatever this is. So if this is like your frequency, so 2 pi divided by w, the angular frequency. So this would actually be 2 pi divided by, and then pi over 2. And then that's going to give you 4 pi all over pi, which equals 4. And so that's what you get as a result. In order to get your fundamental period, it's always 2 pi over whatever term is in front of the independent variable here, when it's written in that specific form, where you have like, you could have like an amplitude here. This is the angular frequency, and then it's like a phase shift added to t. And so now that we talked about that, we're going to get into the power and energy signals now. So these are the big ones that I'm going to emphasize a lot, because I know a lot of people got confused during them. And so power and energy, how do we look at that? So let's just start with the beginning. So energy. So energy, what does that mean? It's basically energy is equal to the integral from infinity to negative infinity, and it's x squared of t dt. So why is the equation written this way? That's probably the most important thing that you need to know. I'm going to show you with my pencil here a common sinusoid wave, right? Well, this is great and all, and you guys are going to say that the area under here is going to cancel with the area under here, right? And so then the total area would be 0 as you keep accumulating, because the positive area would cancel out the negative area. So what we do is we take the square of it, and so that eliminates the issue, and so it would just look something like this. So this would be x squared of t. And so now that we get x squared, if we take the area from negative infinity to infinity, it's going to add all these areas together. So we're actually going to get a value for what's under this curve. However, the issue with this is because it's a repeating signal, it's going to keep having area because this is going to go on forever and ever and ever and ever. So it's going to be infinite, the amount of energy here. Therefore, periodic signals are not energy signals. They are power signals. Okay, now that we talked about that, let's talk about integral absolute value. So the integral absolute value what this is basically from infinity to negative infinity. And this would be x of t dt. And what we have here is basically this is taking the integral of the absolute value. And what this was trying to do for the energy signal was how we took the x squared term here. Instead of doing x squared, what they did for the original sinusoid here is they had it just flipped everything into the positive. So it would look like this as well. There's a difference between when you square it and when you just take the absolute value, specifically because the x squared is going to make it larger than just having the original signal here, with just the x term taking the absolute value of compared to the original. Okay, so now that we talk about integral absolute value, we're going to do average power. And so average power is given by power equals the limit as t goes to infinity, and then it's 1 over the period, and then it's from negative t over 2 to t over 2. And then it's x squared of t dt. And so here, what average power does is it squares it so it gets the signal on the positive domain as we talked about here. And it accounts for the periodic signal by taking one period of it. That's where these bounds are, negative t over 2 to t over 2. That's one period, and it divides it by the entire period in order to give you the average value of that signal. And so that's why it's called average power. And so average, you divide by the total, right? After you sum it together. And the integral is like a sum because it takes it along all the values and adds them together. So it adds all the area, divides it by the total area, and then that's supposed to give you the average power from the signal. And just remember, power is used for periodic signals. They are periodic in nature. Now that we talked about that, we're going to talk about root mean squared. Root mean squared is very similar to the one above. So it's going to be equal to limit as t goes infinity, and what happens is it looks like this. And then you take a whole. So you take the root of the mean, because you do 1 over t, and then you square the inside. That's where root mean squared comes from. You take the root, then you take the mean, and then you square it. And then now average absolute value. Average absolute value is basically limit as t goes to infinity. 1 over t. Negative t over 2 to t over 2. and then it's dt. So this takes the average, and then this is the absolute value. So that's where absolute value comes, and this takes the average of it. And so we keep saying these, and then the maximum value, this is peak or maximum value. Max value. This is going to be max of the signal. So max x of t. That's where you'll see the peak value occur. So basically what we need to say is when the energy is less than infinity, it's an energy signal. When the power is less than infinity, we say it's a power signal. So basically, in an energy signal, the power is equal to 0. But in a power signal, energy is equal to infinity. Because in the periodic, the area, it just keeps increasing and increasing. And so now that we talked about that, the biggest thing you need to know is that periodic signals are power signals, whereas the other signals that don't have periods, they're usually energy signals. And so that's the big thing to take away from here. And now we're going to talk about decaying, converging, bounding, or unbounded. And so what happens between the few is, so let me split this up. You have a signal, so like your signal decays if the signal basically goes to 0 as time goes to infinity. So the signal keeps decreasing, decreasing. A signal converges if that signal goes to a constant value as t goes to infinity. And then a signal is bounded if the maximum value of that signal is less than a constant. Otherwise, it is bounded. It is unbounded if it goes to infinity, the max value of that signal. Infinity. Okay. So the biggest thing is just for decaying, what that looks like in a little graph is basically your signal here just goes to 0. Converging, that signal is going to go to a specific value. So say it's 0 here, and then it just goes, and then it converges to like m, something here, the value along your vertical axis. Bounded, basically, does your signal stay within the maximum value of that signal? So say here, this max value point, it is less than a constant m, because that's one important. The max value does not ever exceed the absolute value of this. It never exceeds or goes to infinity. But it's unbounded, let's say, if the max value of that signal, look right here, goes all the way infinity, that is not going to be bounded. It is unbounded. And so now that we talked about that, we're going to get into the next part where it is impulse signal.
Yo, can you pull the paper out there?
Oh, yeah, sorry. Okay. After this one, we'll take a little break, and then we'll get into the systems part. So this one, lecture 3, is on the impulse signal. And I thought the impulse signal was actually, it is one of the most important things you'll probably learn from this class and take away for impulse. So we're going to go to...
I didn't finish copying it down, whatever.
Oh, shoot. Sorry.
No, it's fine, it's fine. You just go. I'll just. Let's watch the recording.
Lecture 3, which is on impulse signals. So what are impulse signals? And so an impulse signal, it's going to look something like this. And then basically what you have here is it's the delta t, and this is with time. And the signal, what we say here is that the signal goes to, so delta, that's what we represent unit impulse signal, and that goes to infinity at t equals 0. Right here, that arrow indicates that it's going up to infinity. And now the delta t is equal to 0 anywhere else when t is not equal to 0. Because see, anywhere else that delta t does not occur. And the integral of this delta t is equal to 1. And that represents the strength of the signal. And that's why I wrote that 1 right next to it. That indicates the strength of the signal. And another key concept is that delta t is an even function. Okay. So those are the big things to take away from an impulse signal. It's literally just an impulse that goes up to infinity. And where we see this is in circuits when we, flip a switch or something. There's like an instantaneous change in the current being supplied to the circuit, or the voltage now present in the circuit. So that's where you'd see with a capacitor and inductor the effects take place. And so that's where we dealt with when we have our capacitors. There's going to be an instantaneous change basically in the current, and then when we have our inductors, it's going to be an instantaneous change in the voltage. And so now that we talked about that, we're going to focus on 3 properties that I will want to cover very heavily in depth. So listen up. Number 1, so property is the sampling property. And the sampling property, what you need to know from it is that x of t multiplied by delta t minus large T is equal to x, the big T, delta T minus big T. Okay, so let's just draw this out graphically because honestly this equation makes no sense just staring at it. And so a lot of people do a bad job explaining it because literally you just need a picture, go with it. And so here, if we have our x of t, I'm going to just use a different color. So here's my x of t here. And then let's choose the point t where this is going to occur. So here is where delta is going to occur. So this is my delta t minus big T. And what's going to happen is we say this is equivalent because the delta signal, basically it occurs specifically at t and it occurs nowhere else. And so it's 0 everywhere else. So if you multiply these two together, it's 0 everywhere else except at the delta. And remember, when the delta occurs, it is equal to what we like to say. Remember how I said delta goes to infinity when it takes place? Well, we can write that equivalently if we take that sample specifically at that point. It's going to be equal to, and then I'm just going to draw that signal again originally. It's going to be at that point specifically, it's going to be the delta function times the value of the signal at that point. And so here we have the x of large T. And so what does this represent? And so since we talked about here, this is just our signal, right? It can occur, it's basically like this signal's coming by in the unit impulse, the impulse signal right here. It is only taking a value at one point in this specific signal above. So it only occurs in the signal at that one point right here. Anywhere else in it, it doesn't occur. And so everywhere else, the signal multiplied by it is going to be 0. And so what we're going to get as a result is, remember, this delta function has a strength of 1. And so what happens is that strength is going to be multiplied by the point where it's at. And so it's going to produce here x of large T, the point where it occurs. And this represents the strength of the signal at that specific moment. And when this moment takes place, that strength of the signal, it's at delta T minus tau. So that's where this occurs. And so you can think of it sort of as your continuous function going along here, and the delta function occurs at that one point, and that's equal to the delta function occurring at that one point, and then multiplied by the value at that specific time, and that gives you the strength of your signal. And so now that we talked about that, we're going to talk about the sifting property. Sifting property basically tells you in your integral from a to b, you have x of t delta, and then it's t minus large t dt, which is equal to, and then this is x, t, and 0. Okay, this one, I like seeing it graphically. So this is our x of t here again, something like this. So x of t. And then we sample it specifically at t minus tau. And so this is our point t. So this is delta t minus tau. And then when we take the integral under it, that's going to be equal to, remember when we took the integral of the delta signal, that gives you the strength of the signal. So it's going to be, if we take the integral under the curve specifically at this point, what we can do is if we rewrite it, we can see from this property here, let me just show you, this is equal to, right, using the sampling, using the sampling property from above, we can rewrite this as x of t delta t minus tau dt, correct? And then what we're going to do here is our delta, we can take out a negative, so it's t plus large t dt x right? And then remember, delta is an even function. Delta, and so then it's just going to be, oh, sorry, I forgot to flip the order when I took out the negative. This would actually become, and so then this is going to be t minus t. And so then, oh, I'm getting ahead of myself here. Just basically what you need to remember is, I'm just using a different way to derive it. What you need to know is just, as you look at the point where they both intersect, and you take the area under the curve, the area, if we remember, under the delta function gives you the strength of the signal. And now that we know the area under specifically the delta function, that's going to give you the strength of the signal, Recall from the sampling property that this is going to give you that specific time. So if this delta function occurs at that time where t is bounded between a, maybe like a is over here and b is here, if the delta function occurs between that integral, it's going to become 1 here. So this is going to evaluate, because we know x of t is just a point, correct? And so it would be just x of t here.
Can't see.
Oh, I'm sorry. And so,
What are you writing? Yeah, just a little bit out more.
oh, no, ignore this part down here I just said. And so, what we have here, remember how we said, I want you just to look at this point, where we have our bound, and then we have the delta. And look back up at this property here, where we had the bounds and delta, and we said the strength under delta is equal to 1. And so if we, because x of at any particular point is going to be some constant number, so we can take that out, and that's going to give us a to b delta, and then t minus tau dt, and this would evaluate to 1, so it's specifically x of t. If the delta function lies in between a and b. If it does not lie in between a and b, then the delta function, the strength of the signal would be 0 because the delta function would not occur. But if the delta function at capital T occurs between a and b, then the strength of the signal is 1, and that's multiplied by the constant value of the signal. Okay, hopefully that made sense. Did that make sense to you, Tom and Angela?
So like, if it's between A and B, right?
Yeah, if the delta function is between a and b, that means the strength of the signal going back is going to be equal to 1 because the unit impulse occurred. But if it didn't occur, then this would evaluate to 0, so it'd be 0 times x of t, so that's 0
Wait,
otherwise.
strength is just the area
Under the delta unit impulse delta function.
So if it's between A and B, it just equals to 1, right?
Yes.
Oh, okay.
So it'd be 1 times the constant value of what that function is evaluated at time t equals large T.
So it'll be 7? 'Cause it's... Oh wait, that's T, never mind.
Yeah. And so that's what we just get here. We just said that when the delta function occurs between a and b, it's going to be equal to the value of the function at that time t. Otherwise, it's going to be 0 because the delta function did not occur between a and b.
Okay.
And then the third property you need to take away from this, this one's not as common. It's the scaling property. Scaling property says that if we have our delta function, alpha t minus beta, it's going to be equal to 1 over alpha delta t minus beta all over alpha. That's what we have here. And what that basically does is, remember when I told you guys, first you need, here, let me just show you. Delta and then 1 over alpha, what they did here, let me see, 1 over alpha t minus, they did 1 over, oh wait, no. Okay, what they did here in order to simplify it is they had alpha, and then it's t minus beta all over alpha. Okay, so they took out an alpha here, and then it's t minus beta over alpha. And so that's how then, when they took it out specifically here, you can rewrite it when you take out a multiple. 1 over, and then alpha, delta, and then t minus beta over alpha. And so that's how you can rewrite this. So it's telling you you can take a multiple out and do 1 over the multiple times the unit impulse function. And so that's what this third property, the scaling property, is telling you. You can take a scalar out, you just have to do 1 over the scalar. And so that's what we saw there. So we're going to just work through now all the examples on this property because the unit impulse pops up so many times, and you'll see this later on too. Okay, so let's go to the part where we're going to do some examples. And I thought his were really good on it, so we're going to just practice his. So I want to draw these out with you guys. And so examples. Yay! Okay, so it's like samples from Costco, but it's samples. Okay, number 1. 4 to negative 2. Sorry, negative 2 to 4, t plus t squared. Delta function times dt. Okay, so when I look at this, you're probably like, what should I do? I don't know. And I'm probably like the same way. What should I do? Well, the delta function here, let's rewrite this, okay? It becomes t minus 0 dt. Okay? And this represents our t, big T. And so if we were to reference back to the sampling property, you recall that, sorry, not the sampling, it's the second one, which is the sifting. And so sifting involves an integral in it, and it tells us if you have a function multiplied by the delta function, it's going to equal your function evaluated at the when the delta function occurs, if that delta function is between the integral bounds. Well, here, if we draw this out, our integral bounds are negative 2 to 4. That's where we're going to take it under, and our delta function occurs specifically at time 0, right? And so the delta function occurs at time 0, so this is what I'm representing in green. And my integral bounds here between negative 2 and 4. And I have no idea what this t plus t squared is, but I don't care. In this sense, it's just operating as my x of t. So I don't care what the hell that looks like. And so it's just x of t multiplied by the unit impulse, and then that's going to give us, specifically, if that unit impulse occurs, it's going to go back to the sifting property, where we take on the value of that function at where that unit impulse occurs. Sorry. Take on the value of that function, specifically where the impulse occurs. And so here, this is going to be now, since the impulse occurs between the bounds, it's going to be our x of t evaluated where that impulse occurs. So this equation now simplifies to t plus t squared, since the unit impulse occurred. And that value for t we determined was specifically 0. And so what this is going to look like is it's going to be, you can say this is x of t, where our t was 0. And so that is going to be between negative 2 and 4, our integral bounds. Otherwise, it's 0. So it is x is 0 because that's where the unit impulse occurs, from negative 2 to 4. And otherwise, the area would be 0. Okay. Now let's go to the next one, which is going to be from 4 to negative 2, and it's t plus t squared, delta t minus 2, dt. And so this one is occurring at t equals 2. So if we draw it out again, let's do our integral bounds between negative 2 and 4 here. And this is going to be our delta function here, delta t minus 2. So specifically, delta function is occurring here at time 2. And we don't care what our t plus t squared looks like. It's just our x of t. But we can tell that it is going to occur since the unit impulse occurs in this point. So what's going to happen is, remember from that sifting property, and this is going to be t plus t squared. And it's going to be when x is 2 here. Substituting it back in. And so this is going to be then between -2 and t and 4, and then 0 otherwise. And now that we got that, we're going to look at the third one, which is going to be 3 to 4. So from 3 to 4. And it's going to be t plus t squared delta t minus 1 dt. Let's draw it out. Okay, the delta function is going to occur at time equal to 1. And so at time 1, the delta function occurs. We don't care what x of t is here. It can be anything. And now that we determine what x of t is, it can be anything. This unit impulse, though, does not take place between our bounds, which are 3 and 4. Therefore, the signal would be 0 at these, so this would be equal to 0 since the delta function does not occur. And anywhere else, remember, when the delta function does not occur, it's equal to 0. So 0 times this will produce 0. That's how we get the result there. Then we'll go on to 2 more examples here, trying to understand them. Number 4. This is going to be 0 to 3. And it's going to be e to the t minus 2. And it's going to be delta 2t minus 4 dt. That's going to be equal to, let's see, what I would do, remember, because the third property, which is the scaling property, rewrite this, okay? It's going to be delta, and then it's going to be 2. We can take out of the whole thing. And then that would just become 1 over absolute value, whatever it is for the scalar you took out, t minus 2 dt, e to the t minus 2, 0 to 3. Okay, now that we covered that, what we can see here is the unit impulse is going to occur at time equals 2. And so if we draw it out, specifically at time 2, our unit impulse will occur. Our bounds are 0 to 3. And now, since between 0 and 3 the unit impulse occurs, then it's going to be the unit impulse times, and then this is just a constant here, 1 over 2. So that can come out of the integral. We know from calculus, constant can just come out in front. But this is where x of t term is. So that would be e to the t minus 2. I don't care whatever that is. We just know due to the sifting property that this is going to be equal to 1/2, and then it's going to be, let me just rewrite this, 0 to 3, e to the t minus 2, then delta t minus 2 dt. And since our unit impulse did occur between our bounds, it will be, according to the sifting property, e to the, and then it's going to occur specifically at t. This function will occur at that one point. We need to find its value, and then 1/2 times that specific value when it does occur. So 1/2 e to the t minus 2. And since this occurs at time 2, we can just substitute that in here. For the other ones, I wasn't substituting in, but here, and then just it'd be 1/2 e to the 0, which is equal to 1/2. And then for our last one here, number 5, it's going to be t to the negative infinity delta, and then it's going to be tau d tau. And so this is going to be equal to, if we want to think about it, remember how I always said for the delta function, make sure it occurs at time 0 in disguise. That's what it just looks like. And at time 0. So let's draw this out. Our delta function will occur at time 0 here. So that's our delta function occurring. So it's going to be from negative infinity to t. Well, if t is greater than or than 0, it's going to incorporate the delta function, so this will evaluate to 1. If t is less than 0, so let's say it occurs here, if t 1 here, I'm just going to call this t1, negative infinity t1, it does not incorporate the delta function, so it's equal 0. But if it's negative infinity to t2, it's going to incorporate the delta function, so evaluate to 1. And so therefore, what we're going to see is that if it's going to be 1 and 0. So it's going to be 1 if t is greater than 0, and it's going to be 0 if t is less than 0. What this represents is the unit step function, u of t. And so, because that's the common behavior to this unit step. And so, now that we talked about that, I want to just throw in, and this property is just here for a property. Other than that, you don't see that this much, but just have it on your formula sheet in case it ever popped up, because you don't know if it could, but it literally is never used. I've only seen it this one time, and I asked, and even the instructor told us that you don't see this that much. But first, right before that property, just remember that the unit doublet, which is the derivative of the delta function, is just going to be delta function, the derivative of the delta function here. So this is just the unit doublet. Doublet function. And then what you need to know about this, it's an idealized function, and basically there's this weird property that I told you guys you'll see once and never again. X of t, just have this written down on your formula sheet just in case it ever popped up. But it involves the unit doublet function, and it's equal to negative x, so the derivative at time t. And this is if that delta function is between the bounds and that derivative exists. Oh, sorry. There you go. I didn't know. I wasn't showing. But basically, that's what you need to know about the unit doublet. And then the last thing that I think is probably pretty important, besides these 3 properties that we learn for because these are the, I will not emphasize enough, this unit impulse, you need to know by heart. You need to know what this is, because this will pop up in all of electrical engineering. It's just, between, like, when you flip a switch, that's the best way I can describe it. It's just like a sudden impulse in the circuit, current starts to flow. And then, this is basically just saying that as the delta function goes to infinity, it basically goes to infinity when delta function occurs. This is saying that it's equal to 0 everywhere else where the delta function doesn't occur. This is saying that the area under the delta function is equal to the strength of the signal, which is 1, and the delta function is an even function. The 3 properties is the sampling property. If you have your function x of t here, and then the delta function occurs, what's going to happen is it's just going to be evaluated specifically at x, where the delta function occurs, times the delta function. And then here for the sifting property, it's going to be if the delta function occurs in your bounds, it's going to be x evaluated at that point where the delta function occurred, and it's going to be 0 otherwise. The third one's the scaling property, which basically says if you have a scalar in here, you're able to take out, it's going to be 1 over that scalar, and then multiply by that delta function that you simplified. Okay, now that we talked about that, let's get into the last part before we'll take a 5-minute break, or more. Maybe 10 minutes. We'll do like 10 minutes, and then we'll come back. So if you want to grab a snack or something. We have 3 derivatives we need to be familiar with, and their antiderivatives, which will pop up. So let's look at the first one, which is the unit ramp. So remember that looks something like this. I'm just going to use pictures for this. And then we're going to have our unit step. And then we're going to have our next, which is unit impulse. So if we take the derivative of this, and remember this is just like t or something, that's going to produce 1. And so our unit ramp, because remember the slope is just t, the derivative of t is just going to be 1. So derivative of our unit ramp is going to produce the unit step. The derivative of the unit step, well, the only place where a change occurs is at time equals 0. That is a sudden impulse, so that's why we say it's the unit impulse, the derivative of the unit step function. Let's take the antiderivative of this. So the antiderivative now of these 3, going backwards, the antiderivative here of the unit impulse is going to be the unit step, because if we just take the antiderivative of it, that gives us, if I like to think of it the derivative way, then you get the antiderivatives just by doing the opposite way. Derivative of the unit step gives you the unit ramp. And so that's the biggest thing, and just know this is from t to negative infinity, and from t to negative infinity. And then you can add one more derivative to this list if you want to, and that would just be the unit doublet function. So the derivative of the delta function is equal to the unit doublet function. And then the antiderivative of this unit doublet is going to be the delta function. So the antiderivative of the unit doublet, so this is from t negative infinity. Okay? And those are what you need to know for derivatives and antiderivatives. And now we'll take a 10-minute break, so we'll be back at 6:25 if that sounds good. And then I'll see you guys then.
Quick question.
Yeah.
How far are we into like everything we learned so far?
We finished all signals. So we have systems 1 and systems 2. So we have 2 more note packets to go.
So how many percentages do you think for like maybe like 80% done?
We probably did like 70 because we just need to do convolution, which is going to take a long time.
That's it?
Well, no. I mean, convolution will take the longest.
Yeah, so we only have to do convolution after this, right?
No, we have to do a little bit more. LTI systems, remember?
Okay.
Yeah, okay. Okay, so we'll be back at 6:25. Have fun. Sorry, okay. Basically, here for classification of systems right here, we had a voltage divider, and then we had R1, R2. The voltage output is going to be equal to, as we recall from 211, R2 over R1 plus R2 times the voltage input. And then we represent the R2 over R1 plus R2 term here with the system. The input is represented with x to t, and the output's represented with y t. To make a linear system, it has to follow homogeneity, which means if you multiply by a scalar in the input, that's going to produce a scalar multiplied by the output. And then here in additivity, if you add the two signals together, then take it for the system, that's going to be equal to, if you take the system and take it through each of the inputs, then add it together. And then you can combine these two properties into one to show both homogeneity and additivity to prove it's linear. The best way we're going to understand this is by doing examples, and that will be what I will be focusing on right now. So y of t is equal to 3x of t minus 1. And so we're going to have alpha, sorry, what I want you guys to do when you first see this and you're told, is this linear or nonlinear? Get two signals to prove this, okay? And so you're going to get x1 and x2. And basically you're going to run that through, and that's going to produce the output y1 and y2, right? Just goes through, and it's going to produce output y1, and the other one's going to produce y2. And so what we're going to have here, let me actually just move this over to make it easier. Okay, so is this system linear or nonlinear? So we have x1 and x2 as our inputs and produce this outputs y1, y2. Well, we know y1 would be equal to 3x1 of t minus 1. y2 is going to be equal to 3x2 t minus 1. Now we need to, if we're thinking about this, we're like, oh great, what makes a system linear? It has to have homogeneity. So that's the first thing I'm going to try doing, is we're going to multiply this by alpha, which means we have to multiply the whole output by alpha. If we multiply this one by beta, that means we have to multiply the whole output for the second one by beta. Because homogeneity, remember, if you do something to the input, if you multiply it by a constant, it produces the output by a constant. And so here, what happens is, as a result from this, we're going to get alpha y1 is equal to 3 alpha x1 times t minus 1. And then here we're going to get beta y2 is equal to 3 beta x2 t minus 1. Okay, now what we have to do is to make sure that homogeneity and additivity occur. To prove both, now we need to do additivity, so we need to add the two inputs together. So it's going to be this left-hand side added together. So that's going to be alpha x1 plus beta x2. And I'm going to represent that with a dummy variable, zt. And then that's going to produce an output. And my output is going to be, if we look back at the system, it would be just 3, and whatever the input is, t minus 1. Now substitute back for what z represents. So that's going to be 3, and then our z is going to be alpha. So let me do alpha x1, and then that'd be t minus 1 plus beta x2 t minus 1. And distribute the 3, that'd be 3 alpha x1 t minus 1 plus beta x2 t minus 1. And so that's what it's equal to here. So this one down here, where we proved both additivity and we used a homogeneity, we saw that it was equal to, if you add them together, then take it through the system, it's equal to each individual one taken through the system, then add these two together. And when we add these two together, here, what we get as a result is we get 3 alpha x1 t minus 1 plus 3 beta x2 t minus 1. And so what we just saw here is we took it through the system and individually, we took the input signals individually through the system, and it produced this output right here. 3 alpha x1 t minus 1 plus 3 beta x2 t minus 1. Sorry, that highlighter just totally wrecked the result. But I just want to show you that that's equivalent to this statement down here. And this was where we took the two input signals, added them together, then put it through our system. Is remember, what you had to do in order to prove is homogeneity and additivity is right here to prove both. You showed that if you added both together and then took it through the system, that output is going to be equal to taking both individually through the systems respectively and then multiplying them by the scalar. It works both ways. And so that's what we proved right here. Next one, it's going to be example number 2. And so this one would be our, I'm going to do, actually, this one over here. Yeah, this one is non-linear. Linear. Okay, I'm going to then do this one. Yt is equal to tx to t.
Yo, boss, I'm gonna be away for a bit. I mean, I think I already went over this. So.
Okay, yeah, we'll be getting done with this one in about 10. Okay, so to prove this one, we're gonna have two arbitrary input signals, right? x1 and x2. And so what that is going to produce for an output is y1 and y2. And so y1 is going to be equal to t x1 of t, and y2 is going to be equal to t x2 of t. And then if we multiply the inputs, we're going to have to do homogeneity. This is going to be alpha times the entire output and beta times the entire output. This is going to be equal to alpha y1 is equal to alpha t x1 of t. And then this second one here is going to be beta y2 is equal to, and then it'd be beta tx2 of t. And so what we have here, now what you're going to do is you're going to have to do additivity as well. So the two signals, add them together. You're going to get alpha x1 plus beta x2. Approximate this, just use a dummy variable, make this z of t. That output is going to be, substitute in here the input signal, so it would be tz of t. And that is going to be, substitute in what's in for z of t, that would be t. And then it's going to be alpha x1 plus beta x2. That's going to be equal to t alpha x1 plus t beta x2. And now that we see that, we proved here that if you had the two signals, add them together, then put it through the system, this is the output. This is the individual signals put for the system, then added together at the output. And so this would be add these two together. You can get alpha tx1 plus beta tx2. And I notice that these two are equal to each other right here. So that means that this is linear because the two are equal to each other. So this would be linear as well as the one above, linear. Now we're going to step up the complexity a little, so just be a little cautious here. You have to just start small and then see if it works or not. And so this one is going to be a good example. And let's do it. So the first one says dy dt plus 2yt is going to equal t negative infinity to t. Then it's going to be x to tau d tau. And so what that is going to produce specifically is going to be, if it's linear, we can say, well, how do we prove that? We have two input signals, x1 and x2, following the same path. That's going to produce the solution. I'm going to just call this basically a solution to this ordinary differential equation. And so a solution to that ordinary differential equation, I'm just going to rewrite the equation because that's what we mostly look at, the right, whatever the equation is. But the solution to this ordinary differential equation, in the solution to this one, it's going to just be the answer to whatever this is. So you just substitute it back in here. So you have d and then y1 of dt plus 2 y1 of t is equal to, and then this is t to negative infinity x of tau d tau. And then here it is dy2 over dt plus 2y2 t equals t to negative infinity t. And this is x of 2, and because this is x of 1, x of 2, and then tau d tau. And so now we want to do the homogeneity, so we multiply by a constant. This one would be alpha. So then that's going to be alpha times this output, so then alpha times this entire thing here. And then this is going to be beta. And that's going to be beta times this entire thing here. And so let me simplify the first one up here. So bring this one down here. This is going to be d alpha y1 dt plus 2 alpha y1 equals, and then t to negative infinity, and then it's going to be alpha x1 tau d tau. And then the second one here is going to be d beta y2 all over dt plus 2 beta y2 equals t from negative infinity, and then beta x2 t d tau, x2 tau d tau. So add these two outputs together because we will need to see what they produce. So this would be t to negative infinity, since they share common bounds, and it's going to be, alpha x1 tau plus beta x2 tau d tau. And now that we know that, we can write here, since we proved the two, forgot there, we need to also prove it for the additivity. So adding the two signals together, that's going to give us alpha x1 plus beta x2, and all that's going to be z of t which is going to produce our output. And our output is literally going to be, how does it modify this? That's going to be t negative infinity. It's going to be z of tau d tau. Substitute in for z of tau t negative infinity. Alpha x1 plus beta x2 d tau. Does that match with this one? Yes, that matches. So the two are equivalent. Here matches with this one here. Oh, shoot, I wasn't showing any of that. I just proved it using the property we know of. So since the two here are equal, that makes it a linear system. So this is linear. Okay, now that we proved that one, those are just how you prove linearity. So literally, what you do to make sure that you know is you just have two arbitrary signals here. You have x1, x2, then you have your outputs, y1, y2. Well, y1 is going to be equal to specifically the system with the solution to the ordinary differential equation, y2 be the solution to the ordinary differential equation as well. And you multiply each by a specific constant just to show the homogeneity property. And then you rewrite the ordinary differential equations here. You add the right-hand sides together to see how the x variable changes. Then you do the exact same thing with the two systems now added together, and then you just represent it for z of t. You see how that changes the output, and then you substitute back in what you had for z of t here. If this matches the other one here, then it's linear. If not, then it's a nonlinear system. Okay. Now that we have covered linear versus nonlinear, the biggest thing I need to say on linear is that linear systems go through the origin. So nonlinear systems do not go through the origin, and always prove by counter example. That is how you can find out if something is not linear. And so one that I will show you that's nonlinear, so you see one example of it, was example here. Y of t is equal to x of t minus 1. And so you'd have two signals, x1 of t and x2 of t. And that's going to cause the output. So this one would be y1 of t, and the other one's going to be y2 of t. And then what you're going to do as a result here is you're going to see y1 of t, well, that be x1 of t multiplied by x1 of t minus 1, and then this one here would be x2 of t, and then x2 of t minus 1. And then you have to see, after doing these, you have to multiply by a constant. So here it would be alpha, and alpha multiplied by this output here. Then here would be beta. And then you need to add them together. And so if you add the two together, basically to show additivity here. Oh, sorry, you should distribute first. So when you distribute, you would get alpha y1 is equal to alpha x1 plus, sorry, times x1 of t minus 1. And then beta y2 is equal to beta x2, sorry, beta x2, and then x2, oh shoot, I'm forgetting the t's here, that's why it's messing me up. And then t minus 1, close enough, you can understand that. And so then now we have additivity, which you add the two signals here together on the left hand side, you get alpha x1 plus beta x2, and that's going to produce here what you have as a result. We're going to substitute in for it z of t. And so what we're going to see as a result at the output, it's going to be z of t times z of t minus 1. That's going to be, now substitute back in what you have for z of t. That's going to be alpha x1 of t plus beta x2 of t multiplied by alpha x1 t minus 1 plus beta x2 t minus 1. That's what you get as a result for your output here. This does not match the one above if we add it together. Well, let's see. If we add the output here, it's going to be alpha x1 of t times x1 of t minus 1 plus beta x2 of t x2 of t minus 1. So does this match this? No, it does not. And so therefore, if you carried out the multiplication here, it's going to be a FOIL. And so that does not match this, because this would only have 2 terms. This would have 4. So this system here does not match this system. So therefore, this is not linear. A big thing to take into account is how we said linear systems go through the origin. An ordinary differential equation with constant coefficients is linear. That's a big thing to take away. And now that we covered that, we're going to cover time invariant systems. And so time invariant systems are a bit different than linear. They're exactly like it in the amount of work required, but they're more intuitive. So have fun. No, I'm not going to teach you. But time invariant is basically time invariant. So what's going to happen as a result for a time invariant system, that means it's not going to be dependent upon time. You can shift it. So any shift in the output here is going to be represented by shift in the input. So whatever happens to the input shifted is going to equal an equivalent change in the output shifted. So a lot of times we represent it with x of t, and then it goes through a shifting, and then it goes through the actual system, and then produces r y hat of t. And so when it goes through the shifting part here, this is where we have our x of t minus t0, and then it goes through the other system h. And then our other way we can do it is if we have x of t, and then we first put it through the system, then we shift it. And so if we first put it through the system, then we shift it, what we're going to get as a result is y tilde of t. And then this is basically, after it's gone through the system, then we shift it, so that's basically the y t is almost shifted here. And so this is equivalent to h of x of t minus t0, where this is equivalent to y of t minus t0. And so this, a system which is not time invariant is called a time varying system. But in order for a time invariant system, y hat of t must be equal to y tilde of t. And so that's what we have. And now we're going to go off of that a little bit more. So let's do some examples to understand what's linear and what's not linear. And so let's just go with this one here. Example. So it's basically y of t is equal to integral from 0 to t x of tau t tau. What we're going to have here now is basically, let's have our two systems. So if we have x of t passing through, and we shift it, it's going to produce our x of t minus t0, and then it's going to go through the system. In our system here, what's going to happen as a result is it's going to, for output y hat of t, is going to be equal to, then it's 0 to t, then x of tau minus t0 t tau. And if we do it the other way, where we first run it through the system, then we time shift it, what is going to happen, so our output is y tilde of t. That's going to be equal to, and then this is where we actually have the output shifted, so yt minus t0. That's going to be anywhere we see t, we're going to substitute in t minus t0. So this would be t minus t0 here, then x of tau d tau. And so now that we've written those two systems, what we need to see is y hat equal to y tilde? Well, when looking at this from initial glance, looking at these sides here, they don't look equal. However, let's substitute into this one. And so I'm going to rewrite this one as 0 to t. And then what I'm going to do here So I'm going to say lambda is equal to tau minus t0. Then d lambda is equal to d tau. Since t0 is a constant, we don't need to worry about when we take derivative of a constant, it's just 0. So it's 0 to t, and then it's going to be x of lambda d lambda. But remember integral bounds, we have to now, because we adjusted the variable here, we have to adjust the variable in the integral. So it's going to be specifically t minus t0 here, sorry, so I need to adjust this. And then our lower bound 0, so that will stay the same. Wait. Because the lower bound is 0, it's going to be 0 substituted in here, 0 minus t0, so it would be 0 minus t0 here. Okay. Because you have to update your bounds of integration. So you substitute your t, or whatever you have for your bounds of integration, back in for tau. And so, because you're now putting new terms of d lambda. And now that we put this integral here, if this integral, does that look like this integral? Yes, now they look equivalent. So now we can say y hat of t is equal to y tilde of t. So this is a time invariant. So basic covering time invariant, again, what you do is you do a shift in the input, and then you take it through that system, and that produces one output. And then the other way you do it, you take the system fruit first, then you shift it, and then that produces another output. So if y hat is equal to y tilde, and you do just Lua mathematical manipulation, then it's a time invariant system. If not, then it is time varying. Let's do another example. Let's see about this RC system. Okay, so example number 2. RC times dyt dt plus yt is equal to x of t. And so what you do here is we have an arbitrary input x of t. It's going to go through and be shifted in time. And then we're going to take it through our system. So this would be x of t minus t0. Then it's going to go through our system h. And that's going to produce our output, so y hat. And the other way we're going to do it is it's going to be x of t. It's going to first go through our system, which is h. And then it's going to go through time shifting. That's going to produce y tilde. And now that we got that, we need to represent each of these. So y hat means that the term here, this is going to be equivalent to, it only manipulated the x of t term, it didn't manipulate the yt term with time shifting. So since it manipulated only the x of t term, what this is going to produce is just rc dy hat t dt plus y hat t, because y hat is the solution to the ordinary differential equation. Then it's going to be x of t minus t0. The other one is going to be rc dy tilde dt plus y tilde t is equal to, and it's going to be x of t minus t0 as well. So we can see the two equations match up, and that's why we can say an ordinary differential equation, it basically is a time invariant system. Cool. Okay. So we just looked at her xt minus t0 is equal to xt minus t0. Okay, now that we went through that, let's talk about memory and memoryless systems. Okay, so a memory system versus a memoryless. So a system is memoryless if it depends only on present values of the input. And then basically what that is looking at is, let's have an example. Y of t is equal to R2 all over R1 plus R2 times xt, or input. So it's only dependent on the current value here. However, what we would say is this system is memoryless because it only depends on the current value of x. The other ones would be y of t is equal to the derivative of x of t, which is equal to, if you remember, the derivative equation is basically the limit as t goes to 0 because it takes a very little point between the two, and it's the present value minus the past value. And then all dt. So you take the present value minus the past value and you find the difference between the two to give you the derivative. Oh, sorry, this should be the little change in t. And so then because you do the present time and you look at the past time, that's going to be a memory system since it looks at the present and past. The next one is the integral. And if you think about this, it's going to take all the values from negative infinity, so all the past to the present time. And so this is basically a system with memory, because it takes all the values from negative time infinity to the current time t. So this is our present time, where this is very far back, negative infinity. Okay. So that's a system with memory, a system without memory. And so causal systems. A system is causal if the output depends on the present and past values. Of the input. And so what we're going to see is the capacitor depends on present and past values for voltage, temperature right now and yesterday. So a system that's not causal is non-causal or an anticipatory system. And so an example, I guess, would be, again, I guess the right here where it would be yt is equal, let's go back to the voltage divider equation. This would be causal since it depends on the present input. And so, but it is memoryless, we know, but this is causal. The next one would be, let's look at this one. Y of t is equal to 1 over t. T minus t over 2 and t plus t over 2. And then this would be x t dt. Okay, so this would be specifically because this is the length of the signal, which is basically the length of the signal is the large T, what I'm talking about. But this is the present value of the signal T. So here's the present value, T. And because we're looking at the signal right here, if you're adding something to the present value, you're looking at something in the future time. Because you're adding to the time that is the signal's at currently. And then here below is looking at the past time. These are subtracting time from the present signal. So this is non-causal because it looks at the future. It's an anticipatory system. And a system is invertible. This is a big one. System invertible. If the input can be recovered from the output. And so this would be, for example, if we have y t equals x cubed to t. Well, that would be x of t for the input goes through. This would be it cubed. And then we would take the cube root of this. And then that would produce back our x of t. So let's do an example. 3 cubed is 27, and the cube root of 27 then would be 3. Let's try negative 3. Negative 3 is negative 3 times negative 3 times negative 3. That would be negative 27. Cube root of negative 27 is going to be negative 3. So this system is causal. I'm sorry, this system is invertible. And then the next one would be y of t is equal to x squared of t. Well, we have our x of t here. Square it, and then if you take the square root, and then should that produce your x of t back? So here if we square, so for x of t is something like 2, square it, that gives you 4, and then take the square root, that gives you 2. If you have negative 2 squared, that gives you 4, take the square root, that's 2. These two don't match. The x of t input does not give you the original that x of t output. They're not the same, so this is not invertible. Okay. Oh, sorry. Forgot to just show you guys. And now that we talked about that, we're going to talk about if a system is bounded or not. And so remember that a signal is bounded when like the signal is going on and on, but it is under a constant. Like it doesn't go to infinity or negative infinity. A system is stable if every bounded input results in a bounded output. So that's a bounded input, bounded output system. So that means the system is stable. And so basically if you have this system where it's y of t is equal to e to the xt, And is this bounded or not bounded? Well, it has to be less than or equal to, well, let's think. If our x of t is less than m, because that is what, so the max value of our xt, so max value of our xt is going to be less than m, then we can say that, because e is just a number, right? Look on my calculator here. E to the so let me clear this. E to the power of 999. Oh, wait, sorry. Let me just do something smaller, because it can't calculate as many, but e to the power 10, e to the power of 200. You can see e is just a number, and literally it just keeps increasing, but it is a number. And so if it is under a bounded oh, sorry, that was really bad. This thing did not show well. E is just a number. I just was typing in e to the 100, e to the second. But if the maximum is under a constant in this function specifically, and if this is less than or equal to e to the m, then we can say that basically this is bounded. If this is a constant value, then this function here will, or system, I guess I should say, will be bounded as well. Since the input here is bounded, the output should be bounded. So this is bounded. Because the input is bounded, that is why. So our input is bounded if the maximum is less than a constant. So if this is a constant, then a constant, e to the power of a constant is just a number. It is not infinity. Next one is y of t equals x squared of t. Well, if x of t, the max of x of t, is less than some number it approaches, then this would just be m squared. And so then that is just bounded. Then the last one here. It's y of t is equal to, and then it's going to be t negative infinity x of tau d tau. And this is going to be equal to, basically, let's just substitute in something. So let's say x of tau is equal to 1. Because that's a bounded system, right? It's just 1. It doesn't go infinity or negative infinity. So this would be negative infinity to t. This would be 1 t tau. Well, if we take the antiderivative, that's just going to be t from t to negative infinity. So then if we substitute in t minus and then negative infinity, this is just going to be t plus infinity. And so then this would just equal infinity. And so then this is unbounded. Okay. Next. Okay, so that covers all the intro to what a system is. Now we're going to go over convolution and linear time invariant systems, which is a pretty hefty subject for 310. That's a really large topic, and we'll be going over that. So let me pull that up. And this will be the last notes. So what we're going to be going over here for lecture number just lecture on linear time invariant and convolution. Okay, so remember the two properties of the unit impulse function. We have the sampling property, which is basically x of t times the delta function of t minus large t is equal to x, specifically evaluated at that point where the delta function occurs, because it will be 0 elsewhere, times the delta function. Sifting property, which states that from negative infinity to infinity, x of t delta t minus large t dt is going to be equal to, well, the delta function is within the bounds, and it's definitely going to be within the bounds because it's from negative infinity to infinity. It's just going to be x of t. And so now, because it's going to be evaluated specifically at that point and give you the strength of the signal. And then recall that delta t is an even function. And so here, we're going to show you that, let's do an example real quick. From infinity to negative infinity, x of tau delta tau minus t0 d tau. What would this be? Well, looking specifically at the sifting property, this evaluates to x of t0. Next one, we do negative infinity to infinity, and then it'd be x of tau delta t0 minus tau d tau. Well, remember, it's an even function, so can't we rewrite it with a negative? And then this would become actually tau minus t0. Because an even function gives you the exact same thing for the input as the output should be. And then if we rewrite this part to this, what's going to happen now is then wouldn't this just become x of t0? Because this is even, this negative sign won't affect it. And so it's just delta tau minus t0 times x of tau, which goes back up here. And it's just x of t0. You substitute what's in here. And so that's what we did here. That's what we did here as well. Because delta is an even function. Now for the third one, we have infinity to negative infinity, x of tau, delta t minus tau, d tau is going to be equal to, if we think about this, what is it going to be? And so we look and we're like, okay, delta is an even function, we remember, so we can rewrite this as delta negative and then tau minus t. And that should produce the same thing. And so this takes us back to our sifting property up here. And so this is going to be specifically where x is evaluated at that, because that's where the delta function occurs. And so now that we did that, we can say that x of t from here, this is an important result, is it basically just shows that any signal can be written as a sum. And so this is the sum of weighted, this is the weight, time-shifted impulses. And so any signal here, x of t, can be written as a weighted sum, any time-shifted signal here can be written as a sum of weighted time-shifted impulses. And so that's what we have here. And now that we have covered that, we're going to get to the convolution integral coming up soon, and that's going to be a big one. But just to re-emphasize that, because it's so large in all 310, it's the one property you should know, x of t is equal to infinity, negative infinity, and then it's going to be x of tau delta t minus tau t tau. And then what you need to remember is any signal can be written as a sum of weighted time-shifted impulses. And that's where we get it from. So any signal, literally that just means this, can be written as a sum integral of weighted, and then time-shifted impulses. And that's how we derive it right there. Now let's get over to the convolution integral, which basically it will tell you a fair amount. So let me get a new sheet, and let me focus real quick on the linear time invariant system unit impulse response. So to start out, for our convolution integral, we have delta t here. We bring it through a linear time invariant system for any unit impulse. The unit impulse response, which is h of t, unit impulse response, the output of the system is known for any x of t, if we say this. So for an LTI system, because this is the big takeaway, for an LTI system whose response to a unit impulse function delta t is h of t, the response of the system to any arbitrary input signal x of t is, and then it'd be y of t is equal to negative infinity to infinity, and then x of tau h of t minus tau d tau. Okay. Oh, sorry. And now that we covered that, so basically what this means is just any unit impulse we have here through an LTI system will create a unit impulse response. And so that unit impulse response basically will tell us everything about how that system works, and that's the big part of it. And so what we're able to do, because this gives us all the information about the system, this H here for the unit impulse response, we can say that for any input then convoluted with that unit impulse response is going to give us, we know the output, how we can determine that. And so that's because h of t carries all the information about that system. Okay, now that we've covered that, and then what we need to do is prove this. So I'm going to do one of the examples here. I'm going to focus on the second one. And so for this example, it told us, let me do it with this one instead. The unit impulse response which is h of t, is equal to k e to the negative at u of t. And then the input is x of t is equal to a delta t minus b delta t minus 1. So that's our input. And so now, how are we going to calculate the output? So basically, if we know it's in a unit impulse response, you better know off the bat that that means that you have the delta function, and literally that goes through a linear time invariant system, and that's going to produce your h of t. You need to know that. And then that's what, because you have a unit impulse in the response, the output to that is the unit impulse response. Then what you need to know after is, because we know the input and we know the system, how it works, you should be able to determine the output. So yt is going to be equal to the input convoluted with the system. That gives you your output. And so we know that integral is infinity to negative infinity, and then it's going to be x of tau, and then it is going to be h of t minus tau d tau. And now that we know that, we know our input, x of t up here, we can just substitute that in here with tau for every place there's a t, so that would be infinity, negative infinity, going to be a delta tau minus b delta tau minus 1. And then h of t minus tau, that's going to become, well, let's see, this is our h of t up here. So if we're going to substitute in basically t minus tau for it, what we're going to get is, so this is our x of t term here, our h of t term is going to become, let's put in what we have for it. It's going to be k e to the negative a t minus tau u of t minus tau. And now that we have that, just remember d tau at the end of the integral. We need to see, what should we do? Well, we know here, because of the u of t minus tau, that's going to cause specifically one of the integral bounds to be limited. And so what we're going to look at is u of t minus tau is going to be equal to 1 or 0. And it's going to be 1 when t minus tau is greater than 0. And then it's going to be 0 when t minus tau is less than 0. And so then this is going to be, if we solve specifically for tau, that would be when t is greater than tau, and then when t is less than tau, so it'd be 1, 0, same thing just here, just simplified it. And so if we're looking at this specifically on a graph of tau, because we're taking it with respect to tau, let's look at a graph of tau. It's going to be 1 for t, so it's going to be 1 for t greater than tau, and then it's going to be 0 for t less than tau. Time greater than tau, 0 for time less than tau. Hopefully, so when we have a t here, when t is greater than tau, Wait, I think I flipped the axes. Let me check this. And two. This one. Let's see, it's bounded between this and tau. So if we have tau here, it's bounded between, it's going to be 1. It's going to be 1. Yes, and so it's going to be 1. This is tau, and then okay, yes, I am correct on this aspect. When tau is greater than t, it's here. Oh, okay, sorry. I just flip-flopped it. So when tau is greater than t, it is going to be 0 here. But when tau is, when t is greater than tau, so that means tau, I feel like this is easier actually seeing it through this lens over here, sorry. I feel like this is getting really complicated, so I'm sorry if I'm losing you guys a little bit. 1 and 0, and then it's going to be tau is less than t, and then here we're tau is greater than t. Rewrite it this way so it's easier because you take the x-axis and that represents your tau. So when tau is less than t, it's going to be 1. So when tau here is less than t, it's 1, and when it is greater than t, then it's 0. And so this is going to have an upper bound to it because it turns it off and makes it 0. And so this is going to cause specifically our limit of our integral to be up to t, because then after point t it is 0, but before point t it is 1. Then the integral is going to then be from negative infinity to t, and then the rest of it still stays here. So we still have the a delta tau minus b delta tau minus 1 k e to the negative a t minus tau d tau. And now that we have that, we can split it into two integrals to make it easier. So then you're going to have t negative infinity to t, then it's going to be ka, and then e to the negative a t minus tau delta tau minus, and then here it's going to be the integral from negative infinity to tau, and this is going to be kb delta tau minus 1 d tau. Oh, sorry, I forgot d tau on this side. And so now that we got that, what we need to do is we need to get this circuit, this integral. We need to get the constants out of it, and then we need to take the integral of it all. And so if we take the constants out, that's going to give us ka negative infinity to t, and it's going to be e to the negative a t minus tau delta tau d tau minus kb negative infinity to t delta tau minus 1 d tau. And then here we notice that if you just, let me rewrite this right below it, it'd be a to negative at, and then e to the negative positive a tau. And so then we notice that the t term is not going to be affected, so you can take that out as well. So it's actually k a e to negative a t to negative infinity, and e to the a tau delta tau d tau, and then minus k b negative infinity to t delta t minus 1 d tau. And so this, as a result, what you're going to get, when now you take the integral of it, it's going to be k a e to the negative at. And then this is going to be 1 over, oh wait. Remember the integral of the delta function? It's literally the unit impulse function. And so then we can just, if we recall, there's a specific property he used here, which was, just say this is your x of t, right? This is delta of tau minus 0. And, sorry, this is your x of tau. And this is your delta tau minus 0. Then you can use the sifting property. And recall the sifting property. It was basically if you had the bounds from negative infinity to infinity, and it was x of t, and then delta t minus, and then like your t0, whatever, d tau, it's equal to x specifically at that point. And so that's what he did here. And then, so how he took it out and he said e to the a and then evaluated at 0. And then he multiplied it by the unit impulse u of t here. Sorry, not the unit impulse, the unit step. And when we look specifically at that, why is it the unit step function? Why did he include that here? And the reason being is because it's limited to t. So where this is going to turn off specifically, it's going to turn off at t to the upper bound, which is t. I'm thinking it's because we're taking it. It's due to our bounds here, I believe, and that's why. I need to ask him to further that explanation. Let me look at the other one real quick when we simplify it and see if that would help. Because this would be... Should I forget a term here? Maybe... Oh shoot, I forgot to include the term. Just say this was supposed to have... Okay, yeah, this term, it was supposed to have an e to the negative a t minus tau. And then that was supposed to go through, so it should have did e to the negative at, and then it would be infinity to t, and then it would be delta tau minus 1, and then we would have our e to the at as well in here. Sorry, a tau, and it'd be d tau. And so, oh my word, this mathematics, this is getting really long. I don't think this will be on the exam because it's really long, but this would then just, due to the sifting property, this is going to evaluate to e to the a to the 1 because of this right here. And then it's going to be multiplied by u of t minus 1. And then that would be also what carries down is the negative kb e to the negative at multiplied by this. Because that's a constant term, and this is k a e to the negative at. And then e to the a0, that's going to be e to the 0, which is 1. And so then times ut minus that. And that's how you get the specific value here. That's where we solve that. Okay, now that we covered that, what we need to cover last is convolution. And I'm just going to go through one example with this for you guys, and hopefully it makes sense. And then we'll be done with everything. Okay, because this recording is over 3 hours. Okay, let me pause it real quick.